we're going to start off with this definition of a sample space, and that's the set of all possible outcomes of some experiment, or some set of all possible outcomes. So for example, what would be the sample space when you roll a die? It's all possible outcomes. Well, you could just get a 1 spot, 2 spots, 3 spots, 4 spots, 5 spots, or 6 spots. Okay, and the definitions of probability, okay, so the probability of an outcome is the percentage of times one expects that outcome to happen when the process is repeated over and over and over again under the same conditions. That's one way of looking at it. Another way is the probability of an outcome is equal to the number of that outcome over the total number of possibilities. So this would be the total number of possibilities, would be your sample space. And then you just count how many of the outcomes fit your whatever event you're thinking of. So for example, what's the probability of rolling a 5 on a fair die? Well, we just said the total number of possibilities is 6, and how many of these? What's the number that could be 5? Just one of these. So it's just 1/6. And that's pretty easy. So what's the probability? We're going to look at some cards. So what's the probability of getting the Queen of Spades? This is my attempt at a spade here. Okay, so what does a spade really look like? It looks like that. Okay, so the Queen of Spades, there's only one, there's 52 cards in a deck. And there's only one Queen of Spades. Okay, so it's 1 out of 52. Maybe I should write that with cards right here. Cards, okay, there's a 52 total in a deck for those of you who don't play cards. And then there's these 4 suits. And there's 4 suits. And the suits are hearts, diamonds, these spades, and clubs, which look like that. Okay? So the clubs look like a clover. All right, so those are the 4 suits. And there's in each one of these suits, there's 13 cards. So there's like a 2, 3, through 10. And each one, and then there's a jack, a queen, a king, and an ace. So there's 13 in each one of these. So there's 13 cards in each suit. Two through 10, and then jack, queen, king, and ace. All right, so that's the idea. All right, so now, those of you who've never seen a deck of cards. So now what's the probability of drawing a queen? Well, there's 4 queens. There's going to be a queen for each one of these. So the probability of drawing a queen would just be 4 out of the whole sample space, 52. And how about an even number with a fair die? These are really simple. The probability of an even number would be what? The probability of an even number would be, there's 3 even numbers, 2, 4, and 6 out of 6. And you can write that as 3 out of 6 or 1/2. By the way, when you enter your numbers on probabilities on ln kappa, you don't have to reduce fractions. It will accept any equivalent answer. All right. So now probabilities range from 0 to 1, or if we're talking about percents, 0 and 100%. So what is this complement? Okay, so sometimes, okay, so the probability, we'll write this, the probability of A is equal to the probability that A happens. Okay? And then there's something called a complement, and we write it this, the probability of A complement, and that is the probability that A doesn't happen. And we're talking about events that either happen or they don't happen, right? They happen or they don't. So that means that the probability of A plus the probability of A complement is equal to 1 or 100%. All right? So the reason why this is important, you'll see later, is because sometimes one of these is easier. Sometimes A is hard to figure out directly, and so we could figure out A complement, okay? So that's the same thing as saying the probability of A, this is the same thing as the probability of A is equal to 1 or 100% minus the probability of A complement. And if this is easy to figure out and this is hard to figure out, then this is a nice way to do it. In these cases, they're kind of equivalent. So we know that the probability of a 5 is 1/6. So the probability of not a 5, that's the complement, of not a 5, is going to have to be 5/6, 1 minus 1/6. They have to sum to 1. This is very easy to figure out directly, though, because you could figure out directly, there's 6 possibilities, right? 6 of them, and only 5 of them are not 5s. So you could figure that out directly. So same with this. The probability of a queen, we said, is 4 out of 52. So the probability of not queen is going to be 1 minus 4 out of 52, which is 48 out of 52. They're complements. They have to sum 2. This one, again, is easy to figure out, but that's the idea. So now on page later, we're going to see, so it's useful when the probability of A is hard to compute. And the probability of A complement is easy. And that we're going to see examples of that on page 37. We'll see 2 classic examples of that. Okay? Any questions so far? All right, but before we do that, let's look at this key idea in statistics of independence. You're going to see all the time when we make these, the assumptions that we're going to make all the time when we're figuring probabilities is that, like if you're doing sampling, that one draw is independent of the next draw, or that your errors are independent. You're going to see this all the time as an assumption, and it means that what you get on one draw doesn't affect what you get on another draw. For example, if you roll a die, what you get on the second roll is independent of anything you got before. The die has no memory, and just because you got a 1 the first time doesn't influence at all what you're going to get the second time. And so that's true with most gambling games. One exception is cards. So let's look at cards to see the difference between independence and dependence. That is an easy one to think about. So with and without replacement. First of all, 2 events are independent if the probability of the second happening is the same, regardless of whether the first happened or not. And 2 events are dependent if the probability of the second event changes, depending on whether the first event happened. So rolling the dice is always going to be independent, but what you get on one roll does not at all affect what you get on the other. But if you draw without replacement, then the chances change, okay? And if you draw with replacement, they don't. So for example, if you draw 2 cards with replacement, is getting a heart on the second card independent of getting a heart on the first card. So the probability of getting a heart on the second draw is equal to what? There's 52 cards. Whatever I get on that first card, whether it's a heart, there it was a heart, and I stick it back, or it wasn't a heart and I stick it back, does it matter? Does it affect the chances on my second draw? No, there's still 52 cards in here, and there's still 13 hearts in here. So those events are independent. So they're independent. Yes, independent. Because why? Chance is the same. The probability is the same, regardless of what the first card is. Because it's stuck back in the deck. So it becomes just like dice, right? Just like a die. But what about if we do the same thing without replacement? Is getting a heart on the second card independent of getting a heart on the first card? Well, no, it's not. Why? It's dependent. Because the chances change. The probability of a heart on second card if first is a heart is what? Okay, so if the first was a heart, let's pull out a heart. Let's say we got a heart, and we don't put it back in the deck, right? Now there's only 51 cards, and there's only 12 left. But the probability of a heart on second card, if first is not a heart, is equal to what? There's still 51 cards left, but if we pulled out something that wasn't a heart, then how many? We have 13, so they change, okay? So it changes depending on whether the first card is or not. No, dependent, because probability changes depending on whether, depending on whether or not the first card is a heart or not. Okay, so that's the idea. And now there's this multiplication rule, okay? That if two things, okay, so what is the multiplication rule? Where can I put it? All right, so this was the independence. Now, this multiplication rule, oops, right here, this is what I'm talking about. So what is this multiplication rule? That if you want two things to both, if you're looking at the probability that two things both happen, you multiply probabilities, right? If the chance of getting a 5 on the first roll and a 6 on the second roll, if you want both those things to happen, you're going to say 1/6 of the time you get a 5, and then 1/6 of the times that you got, now you've gotten the 5, and 1/6 of those times you might get a 6. So it's 1/6 times 1/6. The probabilities get smaller when you want both things to happen, right? So you'd think, oh, both things to happen, probability of A and B is going to be the probability of A plus B. No, it's the probability. So the multiplication rule is that the probability of, what does it say? The probability that two events will both happen, so that's the probability of A and B both happening, is what? Is equal to the probability the first will happen, the probability that A will happen, times the probability that B will happen, given that A already happened. That says given that A already happened. You read that as probability of B given A. That means the probability of B, that line means given A has happened. Okay, so that's the general rule. But if two events are independent, so if two events are independent, then it can simplify then it will just be the probability of A times the probability of B. Why? Because this, if they're independent, then the probability of B is the same whether A happened or not. Okay? So let's write that down. That's the same thing. So when you have independence, you could use that, but it simplifies. When independent, you get the probability of A and B is equal to just the probability of A. And you don't have to think about whether A happened or not because it doesn't affect the chance of B. Right? Since the probability of this B given A is equal to the probability of B. It doesn't matter. All right? So we can look at this now. And let's look at an example. So a box has what? Let's write it down here. A box has, we have a box in here, and we have tickets, and we're going to shake them up, but it has red, red, and red, 3 reds, 2 blues, and a yellow. Okay? And we mix them all up. And now, what's the probability of drawing 2 blues from the box with replacement? Now, with replacement, they're going to be independent, right? They're going to be independent, so it's just going to be the probability of blue and blue, B and B, sorry. Probability of B and blue is just going to be 2 out of this. There's 6 tickets, and 2 of them are blue, so we get a blue, but we put it back. So it doesn't change anything. So it's just 2 6 times 2 6. You can write it as 1/9 if you want, but you don't have to. All right. And now, but what about without replacement? Then it's dependent. The 2 events are dependent. So the probability of blue and blue changes. It's still 2 out of 6. The first blue is still tied, but now you don't put it back. So you're going to multiply it by something. You're going to multiply it. Now there's only 5 outcomes. And now it matters whether it was blue or not, right? There's only 1 blue left. So this changes. The probability changes. It's dependent. So that's pretty simple. Any questions on that? Okay. So now we're going to go back to these, this idea right here of this complement. Okay, this idea that we're going to look at cases where the probability of A is hard to compute, and we're going to use the complement. So here's 2 useful cases right here. So these are 2 cases where, okay, the probability of at least 1, that's hard to compute directly. So these are 2 useful cases of using the complement. And the probability of none is its complement. Okay, and this is going to be easier. Same with not all and all. So here's an example of this. Let's do the same example here with these 3 red tickets. Whoops, look what I just did. I'm going to put another red. I can put the red there, it doesn't matter. 3 reds, 2 blues, and a yellow. Okay, so now, what's the probability of drawing 2 tickets with replacement and getting at least 1 blue? Okay, at least. So the question here isn't, with replacement makes it kind of easy, but at least 1 blue. So what does at least 1 blue mean? Well, let's think of what we could get here, what our sample space is. We're interested in, well, you could get no blues, 0 blues. You could get 1 blue. This is on 2 draws. Or you could get 2 blues. All right? Now, at least 1 are these 2 possibilities. That's at least 1. You can figure it out directly, but it's harder. Whereas this right here is none, just one way. And none plus at least 1 is going to equal 1, or 100%. So instead of doing this, let's do the complement, okay? Because they have to add up to 1. This one's easy to figure out. This one you could figure out directly, but think about it. You have to figure out, okay, there's 2 ways you can get a blue. You could get a blue on the first, so you could get a blue, and you could do it directly. I'll get a piece of paper if you want to do it. You can do it directly, but you can see what I mean. Okay, so if we wanted to do it directly, it's hard, because what can you get? You could get, here you could get a blue or not blue, or a not blue and then a blue, and then here you could get 2 blues. So you'd have to say, okay, blue is 2 out of 6 times 4 out of 6. Then you'd say, or you'd add those and you'd say, okay, not blue would be 4 out of 6. We put it back times 2 out of 6. And then 2 blues would be 2 out of 6 times 2 out of 6. So you'd add them all up, and what would you get? 8 plus 8, right, plus 4, right? Plus 8 plus 8 is 16, plus 4 is 20. That would be your answer. So you could do it that way, but can you imagine if there were 3 tickets? Then there'd be, how many different ways? There'd be blue, not blue, not blue. There'd be many more possibilities. So an easier way to do this, an easier way to do it, is this is very easy to figure out. So you could say, instead, you could say what? You could say the probability of at least 1 blue, of at least 1 blue, is equal to 1 minus the probability of none. And that's much easier. It's 1 minus. Now, no blues. No blues out of the 6. How many are not blue? On your first, you're drawing 2 tickets. So how many are not blue? 1, 2, 3, 4 are not blue. So it's 4 out of 6. Then you put that not blue back, whatever it was, and the next one is 4 out of 6. So you have the same thing. You have 36 minus 1636. So that turns out to be 20 out of 36. But I think that's certainly faster. And if you had 3 tickets, it would be much faster. Okay? Do you understand why it's easier? Because there's just one way this can happen, and there's multiple ways you can get at least 1. What if we were talking about drawing 5 times? It would be 1, 2, 3, 4, 5. Think about how many possibilities that would be if you wanted to do it directly. Okay, how about let's do the same thing without replacement. So it would be the same thing. How would that change if you do it without replacement? That's the only thing that's changing here. It's the same thing exactly, but this probability of none is going to be what? So now you have the probability of at least 1 blue is equal 1 minus the probability of none. We're doing exactly the same thing. So that's 1. On the first ticket, the probability of not getting a blue is 4 out of 6. But now, let's say we got a yellow. We assume we got it. Now, what's the probability of our next one not being a blue? Well, we only have 5 tickets left, and 3 of them that are not blue. So that would be our answer. So that changes. So these are dependent, and these are independent. But the point that we're making here is whenever you see at least 1, there's many ways that at least 1 could happen. Like, think about it. You have at least 1 child. Well, you could have up to a dozen children. 1, 2, there's lots and lots of different ways that can happen. But the only possibility, the complement is that you have 0 children. So that's much easier to figure out, and then you subtract it from 1. Does that make sense to everyone? Okay, so let's just do another example with all and not all, which is another one. probability of not all. So what's the probability? Let's do this. The probability of getting all reds. Well, that's easy. At least one is hard. Let's do. None is easy. This one's easy, all. Because let's think about all. So let's think about, you either get, this is going to be hard. Because you could get 0 reds. Not getting all means 0 reds, 1 red on 3 tickets, 2 reds, or 3 reds. And not all is all of these. These are not all. And this 3 reds is all. So that one's easy. And together they add up to 1 or 100%. So this one's easy, but look at all the ways you can get not all. So this easy one is what? So this is just going to be the probability of all reds is equal to what? There's 6, and there's 3 reds. So it's just 3, 6 times 3, 6 times 3, 6. But what about not all reds? Well, that's where you're going to have to say the probability of not all is equal to 1 minus the probability of all, which is 1 minus 3, 6 cubed. It's much easier. This would be hard to figure out directly. Okay, any questions on that? So now, let's see what else we need to do. All right, what's the probability of rolling a fair die twice and getting a 5 and then a 6? All right, these are just simple ones. We'll just do these and then, okay, a 5 and then a 6. So the probability, that's 1/6, you multiply times 1/6. What's the probability of drawing 2 cards from a deck with replacement and getting first a heart and then a club? Well, there's 52 cards and there's 13 hearts and there's 13 clubs, but it's with replacement, so it's just that. How about without replacement? Well, this is the probability. Okay, first a heart, it's 13 hearts out of 52. And then you don't replace that heart, so you only have 51 cards left, but you still have 13 clubs left. So that's what it looks like. So this is independent, and this is dependent. All right, so that's it for page 37.